Later in the semester, we will discuss how segments can be created with cluster analysis. For now, let's just assume that we have some segments in the sample and we wish to analyze them to see how they differ from each other. You may observe some differences between the segments, but if you have a small sample, any difference may be illusory, that is due to sampling error. The only way to be sure that the segments are indeed different is by conducting a statistical test. In this video, we will begin our discussion of the statistical tests we need. Our objective here is to understand how segments differ from each other so as to formulate a marketing mix that will appeal to them. There are many ways in which segments could be different in ways that would be important to marketers. For example, how do they differ in the importance consumers attach to various product attributes or to price that would be important in developing a positioning for our products? Do they differ in how much they buy or consume of certain products or brands? Do they differ in what shows they watch, what magazines they read, or radio stations they listen to? How does the profile of heavy users of the product category differ from that of light users? When we want to compare segments, the type of analysis or test we conduct will depend on a couple of factors. First is the dependent variable, that is, what we are comparing the segments on, quantitative or categorical. Second, how many segments do we want to compare? If the variable is quantitative, for example, if we want to compare ratings on a scale or dollar expenditure or purchase quantity across the segments, then we can use a two-sample test of means or ANOVA if we have two segments. If we have more than two segments, then ANOVA is the only option. If the variable is categorical, for example, whether the buyer purchased a particular brand or shopped in a particular type of store, or whether the product was on promotion, then we can run a cross-tabulation, or crosstab for short, regardless of how many segments we have. If we have two segments, we can also run a two-sample test of proportions. However, we will not be covering this test here, as a crosstab can be used instead and will give us the same results. Let's take a deep dive into how to conduct a statistical test for a crosstab. The test that we will use with a crosstab is called a chi-square test. The statistical test with a crosstab is a chi-square test of independence. This is basically a goodness of fit test. That is, it is used whenever you want to see how well an observed frequency distribution fits some hypothesis about the population. Here, we use it to test whether the segments are the same on some categorical variable or different. Since the variable that defines the segments is categorical, that is equivalent to testing whether the two categorical variables are independent of each other. That is, if there is no difference between the segments, the segmentation variable is unrelated to the other variable. So our H0 is that the variables are independent. The alternative is that they are not independent. We use a chi-square test statistic. The basic idea here is that if the variables were independent, we'd expect to see a certain frequency distribution in the table. This is based on the probability of independent events, which says that if two events, A and B, are independent, then the probability that they occur together is the probability of A occurring times the probability of B occurring. Based on this theory, we can calculate the frequency distribution we would expect to see, that is, the expected frequency, and compare it with what we actually see, that is, the observed frequency. Even though SPSS will do all the calculations for us, let's take a look at the reasoning behind calculating expected frequency. Suppose we defined two events as 1. Whether someone is under 30 years old, or 30 and over, and 2. Whether they like Starbucks, yes or no. We want to calculate the expected frequency if the two are independent, that is, if liking for Starbucks does not depend on their age. Here's what a crosstab of the two variables might look like. The columns represent liking for Starbucks, and the rows represent the age groups. The row totals show the number of people in each age group, 100 and 300, and the column totals show the number of people in the like and don't like groups, 200 and 200 respectively. We start by calculating the probability of each group in the sample. There are two groups based on the rows, that is, under 30 and 30 and over, and two groups based on the columns, that is, like Starbucks and does not like Starbucks. We need to calculate the probability of being in each group. How do we do that? Well, that's easy. It's just the number of people in each group divided by the grand total, which is 400. So if we randomly chose a person from this sample, the chances that they would be under 30 is simply 100 over 400 or 0.25. That's the probability of being in that group. Similarly, the probability of being 30 and over is 300 over 400 or 0.75. Using the same logic, you can calculate the expected frequency of people liking and not liking Starbucks. Now let's see how we can use these probabilities to calculate the expected frequency in each cell in the crosstab. Consider the groups age under 30 and likes Starbucks, yes. What is the probability that they occur together, as in the top left cell? We start with the probabilities we just calculated. Remember that the probability of two events occurring together is the product of their individual probabilities if the two events are independent. So the probability of being under 30 and liking Starbucks equals the probability of being under 30 times the probability of liking Starbucks, which is 0.25 times 0.5 or 0.125. In a sample of 400 people, we would expect to see 0.125 times 400 or 50 people in the top left cell. So that's the expected frequency for that cell. We can calculate the expected frequency for each cell in a similar way. Notice that the total of the expected frequency in each row or column always equals the observed total in that row or column. That's because the probability of being in each group is always the same as what we observe. But the distribution of frequency across the cells changes based on the assumption of independent events. If you work it out algebraically, the formula for calculating the expected frequency simplifies to row total times the column total divided by the grand total. Let's look at the data from the national insurance case. The question we want to answer is there a relationship between the education level and willingness to recommend national? The H0 is that there is no relationship, and the alternative is that there is a relationship. Both variables are categorical, that is non-metric, so a crosstab and chi-square test is required. In SPSS, click Analyze, Descriptive Statistics, Crosstabs, highlight REC, the recommendation variable, and move it into the columns field, highlight Ed and move it into the rows field. The image shows what your screen will look like. Next, click Statistics, check chi-square and click Continue. Click Cells, check row percentages and click Continue and OK. Here's the first part of the output, the crosstab itself, with the observed frequencies and row percentages in each cell. But let's hold off on trying to understand what this is telling us. Let's go to the next part of the output and then come back here. The first thing you should look at in the output is the table labeled chi-square tests. The number to focus on in this table is at the top right in the column labeled asympsig, meaning asymptotic significance. This shows the p-value for the chi-square test. Remember, the decision rule for any statistical test is, if the p-value is less than alpha, reject the null hypothesis. This applies here too. We can choose the alpha value to use, so let's use 0.05. Is this p-value less than alpha? Of course it is. 0.019 is certainly less than 0.05. Therefore, we can reject the null. But be careful, there's a warning in the footnote. One cell has an expected count, meaning expected frequency, less than 5. For the chi-square test to be valid, we need each cell in the crosstab to have an expected frequency of at least 5. When this is not true, the chi-square test is considered unreliable and any conclusions from it may be incorrect. This usually happens when the sample size in some of the rows or columns is small. In this crosstab, the sample size in the graduate school row is small, as is the number of people in the no column. When this happens, it's best to reduce the number of rows and columns so that the sample is spread out over fewer cells. We do this by recoding one or both variables to group some of the values together and put them in the same bucket. We'll discuss how to do this in the next video. For now, let's pretend we didn't get this warning and go ahead as if the test showed that the null hypothesis could be rejected. Remember, rejecting the null implies that the variables are not independent. That is, The willingness to recommend national is related to education. That is, it depends on the level of education. Now we can look at the row or column percentages to see how the willingness to recommend varies by the level of education. As you can see, the percent of people in each row that are in the yes column is pretty high for the first three groups, ranging from 89 to 92%, but lower for the graduate school group, about 72%. In other words, grad school educated respondents are less likely to recommend national compared to others with lower education levels. And that's the takeaway from the test. Now, in closing, I want to mention that instead of looking at the row percentages, we could have looked at the column percentages. Both will lead you to the same conclusions, but often one set of numbers is easier to interpret than the other.